Hi, everybody. Welcome back to the power chapter. So, we have already talked about what the basics of power is. Now, we need to make sure that we understand how to calculate it. So, just to remind you, power is the ability for me to get what I want. I want the power. And that means that I want to find that my hypothesis, well, first of all, I want it to be true. And if it is true, I want to be able to reject the null hypothesis. So power is your ability to reject the null hypothesis when the null hypothesis is false. For example, the null hypothesis in the last example was that my love potion doesn't work, right? So I've created this love potion. The null would be it doesn't work. In reality, I want it to work, and I want to be able to have a study that shows that it works. So I want to be able to say it works when it actually works. So I want to reject the null when the null is actually false. That's the power that I want. And we calculated this with a binomial last time, but we can do the same thing with t-statistics that we've already calculated. So in fact, there's power for basically every statistic that we've discussed, but we are going to calculate it for the different t-statistics that we've done so far. Now remember that power is based on several different things, and the ones that we're going to focus on in statistics are number one, the n, the size of the sample, and number two, the effect size, how big of an effect. So remember, in the love potion example, a little effect would be if people fell in love like 1% more than they would normally. A big effect would be if they fell in love, 50% more than they did normally, right? When we think about effect size, we never actually know the effect size. In fact, when we calculate power, technically we should be calculating this power the way we're doing it before you do the study, not after you've already done the study, but before you've done the study. So normally you think about this in terms of like replications, etc. We do it to prepare, to make sure that our study is ready to go, that we have enough people, that we're going to get what we actually want to get, but that we have the power to get what we actually want to get. We don't know if the null is actually true or false, but we want the power to get what we want, okay? The effect size, we never actually know. So I don't know how much my love potion is actually going to make people fall in love. So let's say that instead of measuring whether or not my love potion works based off of whether you're in love or out of love, that's a binomial. Instead, we're going to do it in a continuous way. That is, let's say we're going to rate your love on a scale from 0 to 10. Okay? So a small effect would be, if my love potion makes your love go on up an average, maybe like half a point. Okay? From a you're in love at a 2 now, and then with the love potion, you're at 2.5, that kind of a thing. A big effect size would be if it went up a lot, right? So like, let's say 5 points, right? You were at a 2 before, but now after my love potion, you're at a 7. That's huge. Cohen is a very famous psychologist who created estimates of effect size called Cohen's d. You'll see that a lot. We are going to estimate our effect size using d equals, and this is going to be the same for all of the t statistics. All of them. It's going to seem a little bit different for each one, but this is what it's going to be for all of them. It is mu sub 1 minus mu sub 2 over the standard deviation, which is sigma. So the mean of one group compared to the mean of the other group over the standard deviation. And that's basically what we've been doing up to this point to calculate our t statistics. So let's go ahead and show you how this works, because what we're going to do is we're going to calculate, or we're going to estimate at least, this effect size that we have. We'll do it based off of past data. All right. Then we're going to use a special formula to try and figure out what the actual power would be. So this is to determine effect size, how big of an effect my love potion really had, how big of an effect whatever the variable is has. Okay. So let's go ahead and keep going on this. The steps are going to be, you're going to estimate the effect size, what we just barely saw. How do we do that? Well, we use a prior research guess, right? We use the data from past research, and that's what we're going to do today. We're going to take data that we've already done, and we're going to estimate the effects based off of that. Another way is you just guess, right? You say, well, I don't know. I've never done this love potion before, but my estimation is that it's going to make people really fall in love. Another way is to let Cohen guess for us. Cohen has some estimates of effect sizes, what's a small versus a medium versus a large effect. You can find those in the book if you want to. But first we got to do is estimate the effect size. So we're going to estimate the effect size based off of past research using data from past research, meaning from statistics that we've already run. The second step is to calculate delta. Remember, delta means the change, right? So we're going to calculate the delta that we're going to get, and then we're going to use the table in the back of the book, which tells us based off the delta what our power would be. All right, a power estimate should be. So these are the three steps. We're going to estimate the effect size. That is, we're going to calculate D for everything we do today. We're going to calculate delta based off of that D, and then we are going to use the table to figure out what the power is. Let's start with a single sample t-test. So in order to do this, we have to estimate the effect size. So our estimated effect size, that's the D hat right here. This D is going to be our effect size, is going to be, remember, the mean of one group minus the mean of the other group over the standard deviation. Now, since we don't have all of the population means, we have to use what we do have. So in this case, we're going to use the mean that we calculated, x bar, for our sample, minus the population's mean, because I'm going to give you that for a single sample t-test. I always have to give you a population mean, divided by the standard deviation. Now, in this case, the standard deviation, we don't have the standard deviation of the population. We only have the standard deviation from the sample, and so we're going to use that for our estimate. So we're going to do that. Then we're going to use this times the square root of n, and that's going to give us delta. Then we're going to do the power table. All right? So let me show you with some past data that we have used in previous examples. So let's go for a single sample t-test. Here's some data that we have used in the past. Let's start with this one, actually. Let's do this one first. All right. If you remember, in this case, I want to see if my sample spends more time on Tinder than the population does. All right. In order to do this, then I'm going to need several different things. I'm going to need my sample's mean, my sample's standard deviation, and then I also need the population's mean, which in this case is 35. So I'll just tell you that mu equals 35. So mu is 35 in this case, just to let you know. So if you remember the formula that we want, I'm going to go ahead and show you the formula while we do this. The formula, come back formula, the formula is going to be x bar minus the mu of the population over the standard deviation. So this is going to be the estimate of the effect size. So x bar is the mean of the sample, which in this case is 20.91667, minus the mean of the population, that's mu, which is 35. Well, guess what? We already had to do that anyway when we were calculating t. That's this one right here, x bar minus mu. That's this, okay? So that numerator is the same as when you're calculating the t. But now, instead of dividing it by the standard deviation divided by the square root of n, we're just going to divide it by the standard deviation, which is right there. So the effect size that we are estimating is going to be, so let's go ahead and put the equal sign, is the mean minus the sample's mean in this case, minus the population's mean divided by the sample's standard deviation. That's it. And you get negative 1.05106, okay? We then take this one and divide this by the square root of n. Now, we already have the square root of n over here because we had to do it before for the other things, right, for calculating t. But just to get it again, just to make sure that you know what we're talking about, square root of n is going to be the square root of all the people in the sample, which is 12, 3.46102, which obviously is the same thing right there. All right. Now, instead of dividing the effect size by the square root of n, I'm going to multiply the effect size by the square root of n. And I'm going to get lowercase delta. That's what that squiggly weirdness looks like, is the lowercase delta. It is the estimated effect size, whoops, not divided, times square root of n. When you do this, we get a delta of negative 3.64. Then we take this negative 3.64 and we use the table in the book to figure out what our estimate of power is going to be. The table in the back of the book looks like this. This is the table. And what you're doing here is, this is power as a function of delta and significance level. So the significance level that we want is alpha equals 0.05. These are the deltas over here. Now remember, the delta that we calculated is, let's just remind ourselves, because I honestly forgot, negative 3.64. Now you do not care about the negative in this case. It could go negative or positive, don't worry about that. It's not a big deal. We got a negative 3.64, so let's add some notes in this one and I'll show you. The delta that we got was negative 3.64. And so we're going to use our closest estimate of delta, which is right there. And this column right here is going to be alpha equals 0.05. So negative 3.60, that's the one we're going to use. So just we're going to be conservative on the estimate. So we're not going to round up, we're going to round down when we do that one. 0.95 is our delta. Sorry, 0.95 is our power. Delta was 3.64, but the power is 0.95. That means that if the null hypothesis is actually false, then the ability for me to reject the null hypothesis would be 0.95, a 95% chance of rejecting the null hypothesis. All right, so now what I want you to do is I want you to try this on your own. I want you to calculate delta, calculate the estimated effect size, calculate delta, and then use the table to figure out what the power estimate is going to be. And so I want you to use these numbers right here. So let me show you. Okay, so this is old data that we've used as well. So this is the sample, 6 people in this particular case, 6 people. And once again, mu is going to be 35 in the same way, all right? Mu is going to be 35. So if mu is 35, then I want you to calculate the estimated effect size, delta, and power for these data right here. When mu equals 35 and alpha, so alpha equals 0.05 in a two-tailed test, which is what we have on this table. It's always going to be a two-tailed test. So calculate it now. Okay, now remember to calculate this, let's go ahead and put up the everything that we need right here. So we are going to have the mean minus mu over the standard deviation. So effect size is going to be the sample's mean minus mu, the population's mean, divided by the standard deviation, which is the standard deviation of the sample. This is our estimated effect size. Delta is going to be this times the square root of n. So it's going to be this effect size, estimated effect size, times square root of n, and n in this particular case is 6, 1.04. Then once we have those, we look at the table to estimate power. And so let me put this power table over here on the side so we can see it at the same time. Delta is 1.04. So we look up here, get as close of a delta as we possibly can. 1.04, we're going to round down. Okay, round down. 1.0. Alpha for a two-tailed test, 0.05, and then our estimate of power is right here, 0.7, excuse me, 0.17, 0.17. That means that if my hypothesis is correct, then I only have a 17% chance of rejecting the null hypothesis. That's what power means. So in this particular case, my hypothesis was that my students spend more time on Tinder than the normal population. Well, in this case, the normal population spends 35 minutes on Tinder. That was mu right here. My students spend an average of 44.167 minutes on Tinder, and the standard deviation was 21.54 minutes. When we put that all together, that is, if my students actually do spend more time on Tinder, then with this sample of only 6 people and the effect size that we found before, I only have a 17% chance of being able to reject the null hypothesis, even if my hypothesis is correct in real life. Let's go ahead and go to an estimate for, let's move ahead. Where is there's paired. Sorry, I went too far. The effect size, let's go ahead and go to the effect size for a paired samples t-test. So now remember, in this case, mu sub 1 minus mu sub 2 over standard deviation, in this case, we're talking about the standard deviation of the difference. And remember, when we're talking about a paired samples t-test, mu sub 2, that is the null hypothesis, is 0, that we don't think there is any difference. So that means all we need to do is look at the average of the difference that we calculated over standard deviation of the differences. And then we do the same process that we did before. So let's go ahead and find some data from the previous example that we've done. There's paired samples. Let's go ahead and start with this one. This will be good. So if you remember, I thought that people's GPAs increase over time if they study, right? If they study. So here's the data, your GPA at time 1, and then everybody studied, and their GPA at time 2, right? Now remember, what we're looking for is not the mean of GPA 1 and the mean of GPA 2. That's not what we're looking for when we're talking about a paired samples t-test. We need to find the difference between GPA 1 and GPA 2. So this is what we're talking about when we're discussing these things. So the mean sub d bar is this. This is the average of the differences. And then we need to divide that by the standard deviation of the differences, which is right there. So let's go ahead and do this calculation right now. So we need to get our, I'm going to scroll this over so we can see it just a little bit better. We are going to get our estimated effect size, big letters, which is going to be the mean of the differences divided by the standard deviation of the differences, 0.952. Then we need to find delta. Delta is going to be this effect size, right? This effect size times the square root of n. So the square root of n, and in this case, n is the number of differences that I have. I have 10 people, that means I have 10 differences. 3.012. Then I look at 3.012 on the table. So I'll move it over even more so that we can see the table and this at the same time. 3.012 is closest to 3.00. Alpha equals 0.05, and we do a two-tailed test. I'm always going to do that for this one. Always going to do that. And I get a 0.85. 0.85. 0.85, if you want to see it up higher. 3.0, alpha 0.05, 0.85. That means that with 10 people and the data that I have in the past, my power estimate is 0.85. I have an 85% chance of rejecting the null hypothesis if studying actually does help your GPA. So if studying actually does help your GPA, this study has an 85% chance of finding it. That's what that finds. Okay, now I want you to try it on your own. Start with these data right here. So go ahead and just look at these. That's the deviation. Sorry, let's try this again. There we go. Okay, now I want you to try it on your own using these data. So my hypothesis is that listening to the psychology stats lectures makes people more hungry. So this is hunger before they listen to the lecture, hunger after they listen to the lecture. Here are the differences. Go ahead and calculate the estimated effect size, delta, and power. Okay, so for this, it's paired samples. So the effect size is just going to be the mean of the differences divided by the standard deviation of the differences. Then delta is this effect size times the square root of n. Guess what? I already have the square root of n right there. There's 9 people, so the square root of n is going to be 3. Then I look up delta 1.33 on my table. Closest I have is 1.3. Alpha is 0.05. And therefore, this is my power estimate right here, 0.26. 0.26. So power is 0.26. So that means that, remember, my hypothesis is that listening to stats lectures makes you hungry. So if I had these data with their effect size and only 9 people, even if stats lectures really did make you hungry, I would only have a 26% chance of rejecting the null hypothesis.